talk is about 10 minutes long, 2 minutes for questions, and just look for me, and I'll sort of signal to you when the 10 minutes is up so that you know you need to finish your thoughts. So the first talk today is on non-contact ultrasound imaging applied to cortical bone. Okay, so you're ready? Let's go ahead and start.
Good afternoon. My name is Peter Halcrow, and on behalf of Dr. Gnazer and Dr. Bullman, I'd like to present you this project on non-contact ultrasound applied to cortical bone phantoms. To give you a brief overview, ultrasound has been used for field imaging. It's also used in tumor responses to radiotherapy, etc. But an emerging field is osteoporosis, and what I mean is detection and management, as well as determining fracture risk. Quantitative ultrasound studies of bone quality, well, they involve contact ultrasound. That means that the transducer itself, by utilizing coupling gels, makes contact with the subject. And they have found good results in comparison to radiation methods, including DEXA and QCT. And it was this graph that was published in 1984 by Langdon, Palmer, and Porter that really ignited the interest of scientists to study ultrasound and bone analysis, especially for osteoporosis. And as you can see from this figure, that what they determined is you increase the frequency, the higher frequencies, there's a separation of attenuation between healthy bone and unhealthy bones. So that ignited the interest of the science to pursue ultrasound in bone analysis. However, we come to this innovative study, which is in the study itself, non-contact ultrasound. There's several benefits that if you're able to provide or show the capability of non-contact ultrasound to determine osteoporosis or osteoporotic patients. Some of the motivations behind this innovative study of non-contact ultrasound include, well, detecting osteoporosis, which would eliminate harmful ionizing radiation methods. Well, you think to yourself, well, the contact ultrasound does that already. Well, it would also eliminate the use of gels. And gels have been known to be allergic to certain patients. And I've read recently in certain papers that these coupling gels have been known to cause pneumonia and infections, and they're also temperature dependent, so that there's a sort of error that's associated with these coupling gels. And non-contact ultrasound would eliminate the use of these coupling gels. It would also eliminate pressure-dependent readings of the contact method. When I apply a transducer to a subject, I'm going to get different readings when you apply a transducer to a subject because we're going to apply different pressures. So it's operator. So the contact method is operating dependent. And non-contact would eliminate that. It also extend non-contact ultrasound to other applications where contact ultrasound would be painful or harmful, such as burn patients, the eyeball. I presented a paper in Vancouver this past July, and a company in Los Angeles called Utopia Compressions Corporation actually contacted me because they saw my published abstract. And I'm now working with this company, and they're doing pulse echo mode in ultrasound to determine, to analyze burn patients. This is our system. As you see here, we have an upper transducer which transmits the signal, and we have a lower transducer which receives the signal. We also have a scanning system, and with pre-programmed software, the transducers operate autonomously, and therefore we can replicate and reproduce measurements without human error. Here's the bone phantoms that we use for our study. We have 17 different bone phantoms made by this company in Virginia, CIRS, and each bone phantom has its own calibrated bone mineral density. And the range of our phantoms in density are the same range of the human skeleton. Phantoms that we're studying. Measured parameters include attenuation, speed of sound, time of flight, thickness of bone phantoms, integrated acoustic response, which is the total power signal, And as far as results, let's start off with speed of sound. Now, speed of sound versus density. As you clearly see, as you increase the density of our phantoms, the speed of sound increases. Now, this is a very unique graph because this compares the contact method, which is conventional, with the non-contact. The square data points were actually taken with our system in the contact mode. And the trend line that we get is 0.96, and our square value of 0.96. Then we took our same system with these other data points and ran the same measurements. And with this solid trend line is the non-contact correlation, which we get is 0.94. So this graph validates that non-contact ultrasound can have or produce measurements similar or as accurately as the contact method, which is used in clinics today. Another thing we measure is integrated response. And as you see, over a range of densities, as density increases, the IR, or integrated response, decreases. And these are data points that were taken over a number of several days. And you see the high R squared values. Here's some color-coded attenuation images that we take with our scanning system. And the image in the upper left here is our lower end density phantom, about 150 milligrams per cc, and in the bottom right is a phantom of 600 milligrams per cc. As you clearly see from the color-coded images, that as you increase density, you also increase attenuation. Another thing we measure is what we call broadband ultrasound attenuation. Now the way you get that is you take the amplitude over a range of frequencies, and you get a positive linear slope here. And the slope is actually the broadband ultrasound attenuation, which is decibels per megahertz. Now you take that slope of attenuation and you plot it versus bone mineral density. Now this graph actually is in the contact mode. This is data that we collected in the contact mode. And as you see, if we plot the BUA, the broadband ultrasound attenuation versus BMD, you get this positive linear slope with an R squared value of 0.9797. So as density increases, the BUA increases as well. And recently, I did the same measurements in the non-contact mode. Now, I plotted BUA versus bone mineral density. And as you can see, I get a positive linear slope with an R squared value of 0.9615. Now, what this is saying is that I get similar results for the contact mode, which is used in clinics today. I can get the similar results in the non-contact mode. And this is really a key figure in this speech, because if you can calculate the BUA, then you can determine bone mineral density. So if I also take a patient with osteoporosis and calculate the BUA, I can determine bone mineral density, and therefore I can determine whether a patient is osteoporosis or not. Future studies, last few slides here, future studies of non-contact, well, we're currently working on a grant proposal seeking human approvals. We are human subject certified. We'll be collecting data from phalanges, which has been successful at anatomical point at this point. We'll collect quantitative data for osteo products and have a control group for non-osteo products. In conclusion, promising aspects of NCU, well, non-ionizing radiation, non-invasive diagnostic where contact method is painful or harmful, rapid diagnostics, eliminates pressure-dependent readings, eliminates the use of coupling gels, and NCU might find a wide range of applications in the medical field in the near future.
We definitely have some time for questions.
What kind of transducers are you using?
We have our non-contact transducers are air coupled, and the mean frequency ranges anywhere from 350 kilohertz to about 1.5.
Yeah, they're air coupled. What are they? Are they piezoelectric? Tuned? What?
Yeah, piezoelectric.
In the historical data you showed attenuation versus frequency for healthy bone versus osteoporotic bone. The healthy bone showed a lot of structure there, which seemed to be not entirely random, whereas the diseased bone was smooth. Is that due to resonances? Or it's right near the very beginning there. Is that to be believed, or what's the origin of that?
Let's see. This one here?
Yeah.
So you're talking about
there seems to be some significant structure. It's not simply random there.
Well, I didn't collect this I didn't personally collect this data. This was from Lang's paper in 1984. But some possible reasons for these fluctuations and points are not smooth as you get here could be the higher densities. The higher impedance mismatches could cause some error associated with higher frequencies, at higher frequencies.
So it's an error, not something that would be reproducible if you were going to go back and do the scan again and again.
Well, I imagine if you redid this over and over again, you would get similar results.
Okay.
Yeah. But as far as, say this point to this point, I mean, I'm sure that would probably vary.
So I think that's all we have for today. Thank you very much.
Thank you.